Last time we met, we were talking about the fact that we can alter substances just simply by putting another substance on the surface, surface treatments. We use paint. Thin films is another example of that. But sometimes the easiest thing to do is by just adding a thin film of a metal on the surface of another material. Okay? Spencer, you seem like a truck kind of guy. Do you have a truck? Do you have a chrome bumper? Okay. Is it all metal or is it really? So it's an older truck. Okay. Most of the newer trucks, you know, have a chrome surface. It has a chrome thin film on the bumper when it's probably just fiberglass. So today I'm going to explain to you how they get that chrome on the surface through electroplating. The process of using electricity to deposit metal ions onto another metal. And also, you can also deposit it onto stuff that's not even metallic these days as well. The act of electroplating is called electrolysis. 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 I know, I'm going to skip 11. I'll come back to it. Okay, so what does it mean for a metal to be oxidized? Oil rig. What does that mean? It loses electrons. So copper, when it is oxidized, will lose 2 electrons to become copper plus 2. What does it mean for a substance to be reduced? Oil rig. What does it mean for a substance to be reduced? Gain electrons. So when copper gains 2 electrons, it is reduced. What are some examples of electroplated substances? Coins. A penny is electroplated. It has a thin film of copper. Metal bumpers are coated with chromium and nickel in order to make them shiny. Some of your jewelry, girls, are going to be plated. Believe it or not, I used to be a thin guy. I used to weigh 165 pounds when I got married. That was 60 pounds ago. Okay? In that time, I grew enough so that my ring stopped fitting on my finger. So at that time, my wife decided to buy me a temporary ring until we can get ours resized. And she went to Walmart and she got a $20 gold ring. Gold plated ring. So what does that mean? It means it's probably just a piece of iron with a thin film of gold. Okay, so what happened after about 6 or 7 months?
It turned silver.
The gold wears off. Just from wear and tear, the gold wears off. And that's the problem with these thin films. A lot of times they're really, really thin. So, where do the electrons come from in order to reduce things? Electroplating can only occur if you hook it up to some kind of electron source, whether it's a battery or just an outlet. Now here are the steps to electroplating, and I'll show you 2 different videos in order to illustrate this. Okay, there are going to be 3 steps here, and then in the next slide there'll be 2 more steps. So you'll need to be patient. So let's say you have a metallic piece of jewelry, earrings that you really, really like, but you'd love to see it in gold. So what you would need is you would need to get a solution of gold solution. Okay? So you get a solution containing gold in the form of ions. You immerse a metal rod into the same kind of metal. This is called the anode. Okay, this is called the anode. The electrons are going to flow toward, well, the electrons are going to flow from it. You need to, the thing about batteries is that they release electricity. They release electrons, but they need to get them back. Now, they don't care where they come back from, but they do need to get them back. They need them back. That's the deal with batteries. So you connect the anode to a battery supply. That will basically supply the battery back with electrons.
How much is gold solution?
It's actually pretty expensive. You connect the battery or the power supply to the metal to be plated, so the electrons will come out of the battery and basically fill up her necklace. Not necklace, her earrings that she wanted to plate out, right? Her earrings. So the earrings will become super negative. Turn on the power. Well, let me show you. You power up and voila. That's the 5th point. And then I'll show you how this works. Okay, so this is what you want to plate out, right? Okay, so what you have here is copper ions, and this is called the anode. Electrons come out of the anode and they flow toward the cathode. What you want to remember is red cat. Reduction always takes place in the cathode. So, because all metals want to lose their electrons, here comes electrons from the anode. When it goes into the battery, it pushes out electrons from the other side. So here comes electrons. So the electrons are going to surround and flow through her earring, making her earring really, really negative. With her earring really, really negative, let's make this into gold. The gold positive ions will flow and be attracted to her earring. When it touches her earring, it picks up 2 electrons, and that gold sticks to her earring. After several hours of doing this, you will have several layers of gold on top of her iron earrings. Okay, so that's how it works. Over time, the copper begins to fill this up and it'll ruin the solution. So you can't do this for long periods of time. You have to do it for a very short period of time. So let me show you an animation with this at work. Okay, so you have water, a little bit of vinegar. It needs to have ions in it. Here's the copper. The copper sulfate, which should be SO4. She made a mistake here. All of these should be SO4. Okay, so you have copper. This is where the electrons are going to come from. You hook it up to the positive side of the battery. So electrons are going to come out of here into the battery, pushing electrons the other side. This piece of metal is going to fill up with negative ions or negative electrons, making it negative. Are the negative ions going to be attracted to a negative pole? No. Okay? The positive ones are. So the positives are going to come over here, touch it, and pick up the electrons and stick. Watch. They misspelled loses. So here comes the electrons. And the electrons are pushed. Sticks. So now you have a little piece of copper that's stuck on that metal. And it keeps going. Another piece of copper. keeps going. Over time, that metal is going to fill with layers of copper.
That looks really gross.
Okay, the next video, this kid is adorable. Watch.
This is Conventure TV. We are going to do it about my science project for my science fair. And we're going to do it on electroplating, turning like a penny into zinc. We are going to be using this for the vinegar solution. We're going to have this battery and some alligator clips or crocodile clips, whatever they're called, connected to the wire. The wire's going to be connected to some of the metal. We're going to plate it on one of the coins, and then we're going to make the coins a different metal. So let's start. We're dissolving zinc in vinegar to start the solution. Here is the soul of it. Well, now we're going to pour the vinegar into the bottle I showed you.
Careful.
Whoa. Now, to finish the vinegar solution, we are going to use Epsom salt to help the solution work, and we're going to use sugar to help the Epsom salt not grow crystals, so it makes a better electroplating solution.
The kid is probably reading the words from a cue card.
Stir, stir, stir. Looking good. Now in our solution, we have Epsom salt, sugar, and zinc, so you might not want to drink this. Please don't, because... And now we are going to unleash the battery. Never touch the two springs of the battery at the same time, and use the red alligator clip is what you see here. Always put it on the positive, and use the black one and put it on the negative. This is the zinc on the anode, and this is a copper penny on the cathode. I'm a little nervous holding these because I accidentally put them together, dropped them, put it together, and I saw some electricity, and that sounds impossible. I'm going to put the zinc anode into the solution. Now we're going to put the penny cathode, the copper cathode, in there. I think this is very dangerous. Check it out, it's bubbling. Now we're going to wait a couple of minutes to see what will happen to this. Thumbs up. It's time to check it out and see how it's doing. See how it's doing. Whoa, we have a zinc penny. Look, a zinc penny, just as we were expecting. We had this regular penny, and now we turn it into zinc. Isn't that amazing? Have you ever seen a zinc penny before? And electroplating is used for a lot of things, putting metals on other metals, because like other coins that we have are really just coins that are copper, but they were plated. Thanks for watching this. Please visit my website, conventure.tv, and my Twitter account name is @JonasArcher. Thank you. Bye.
Wasn't he great? Is that not the best science video you have ever seen in your life?
Bill Nye isn't.
Bill Nye's better than this kid? He's not as cute.
So?
So, what happens at the anode? Oxidation. Here's another way of looking at it. With this anode cathode, all you need to remember is red cat. Red cat. What happens at the cathode? Reduction. So if you're at the anode, oxidation. So at the anode, electrons are released. Electrons are released. He had a copper anode where electrons were released. Copper metals give electrons and then dissolve into the solution. These electrons had to go where? Where did it go in his example?
To the
Battery. It has to go back, it has to go into the battery in order to push electrons into the cathode. It has to go to the battery in order to push electrons into the cathode. What happens at the cathode? You need to remember red cat. Red cat. Reduction happens at the cathode. So that's where the zinc that he had dissolved in the solution played it out on the cathode. It picked up electrons and it stuck on the cathode pennies. Electrons are picked up by the zinc. That's wrong. Should be zinc. Zinc ions in the solution and played out on the metal. Is plating an example of chemical or physical reactions? Actually, it's chemical. The metals that get plated are actually bonding with the metal that's being plated from. It is kind of a weird chemical reaction because there are electrons being transferred. So there is a change. There is a change in properties. The most common type of electrochemical cell, that's electrolysis. You guys are not you're used to playing around with things that are a result of electroplating, but you're not used to electroplating. You're used to batteries or voltaic or galvanic cells. That's what you're used to playing around with. So how does a battery work? What is a voltaic cell? A voltaic cell is a chemical reaction that gets electrons in a redox reaction to work for us before they finish the reaction. The common name for a voltaic cell is a battery. So, what happens at the anode? What acronym did I ask you to remember?
Cat. Red cat.
Red cat. So, if reduction happens at the cathode, at the anode, oxidation. Electrons from a sheet of metal that is higher on the activity series leaves it and flows out by way of the wire.
It's all going to lead up to a lab we're going to do.
Yes.
Aha.
Is it
tomorrow. What does the electrons do? What do the electrons, right? What do the electrons? What does the electron do then? They flow out looking to reduce someone. In the meantime, they will power your calculators, they'll power your iPhones, they'll power your flashlights and your Game Boys and your Wii remotes, your Wiimotes, right? Your Wiimotes. So they do work for us on their way to find somebody to reduce. Where will they find somebody to reduce? On the other side. So on one side of a battery, you're going to have a metal that wants to give electrons. On the other side of a battery, you'll have something that wants to take them in. So on one side of the battery, the electrons are released. It's called the anode. Then they do their job, and then they come back, and they will reduce somebody in the cathode. They will reduce somebody in the cathode. They will reduce somebody in the cathode. What does a salt bridge do? It makes sure that all the positive and negative ions even out. It makes sure that all the positive and negative ions even out. At the anode, too many positive ions are made, so the negative ions tend to flow in there to cancel out. At the cathode, too many positive ions are made, so the positive ions flow there to replenish them. So a salt bridge helps to even everything out. All right, let me show you.
Let's zoom into the atomic scale and see how this cell operates. Here, at the anode, the site of oxidation, zinc atoms in the metal bar are in contact with the surrounding electrolyte solution. Each atom loses 2 electrons and becomes a zinc ion, which diffuses into the solution. The electrons given up enter the bar and join the flow of electrons up toward the external circuit. They travel through the wire and flow into the cathode, the site of reduction. When a copper-2 ion in the cathode solution makes contact with the copper electrode, it gains 2 electrons and is reduced to a copper atom, which deposits on the bar. Therefore, as the cell runs, the zinc anode becomes lighter and the copper cathode heavier. Now let's close in to see the role of the salt bridge. The non-reactive sodium and nitrate ions of the salt bridge prevent the buildup of charge that would occur as zinc ions enter the anode solution and copper-2 ions leave the cathode solution. Such a charge buildup would halt cell operation. In the anode compartment, nitrate ions leave the salt bridge to balance the gain of positive charge as zinc ions enter the solution. Some zinc ions also enter the salt bridge. In the cathode compartment, sodium ions leave the salt bridge and nitrate ions enter it to balance the loss of positive charge as copper-2 ions leave the solution and are reduced at the cathode.
What are batteries? Can you imagine a world where all electrical appliances had to be plugged in? Flashlights, cell phones and toys would be tethered to electrical outlets, making them clumsy and inconvenient. Batteries provide portable, convenient sources of energy for powering devices without wires or cables. A dry cell is a common type of battery used today. It basically converts stored chemical energy into electrical energy. In the most basic terms, a battery cell is made up of three components: an anode, a cathode, and the electrolyte. In the dry cell, zinc is the anode, the graphite core is the cathode, and ammonium chloride paste acts as an electrolyte. Due to a chemical reaction within the battery, the anode builds up an excess of electrons. This causes an electrical difference between the anode and the cathode. The electrons want to rearrange themselves and displace the extra electrons in the cathode. However, the electrolyte ensures that the electrons cannot travel directly to the cathode. When the circuit is closed with the help of a conductive path between the anode and cathode, the electrons are able to travel to the cathode. This in turn provides power to any appliance placed along the way. Over time, this electrochemical process alters the chemical makeup in the anode and cathode, and eventually they stop providing electrons. And this
Your
is how
battery
a
dies
battery
when
dies.
one side of the battery loses all of its electrons.
Batteries provide us with a mobile source of power that makes many modern conveniences possible.
Alright, so you need to pause the video and very quickly draw this because we're about to write on it. Alright, here we go. So the anode is going to be made up of a metal that easily loses electrons. Maybe not necessarily easily, but will lose electrons. So anode is your electron maker. In the anode, copper ions will be made by the loss of 2 electrons. So in the anode, copper solid becomes copper dissolved, copper 2, and 2 electrons are made. Oxidation occurs in the anode. Remember, red cat is the key thing to remember. Reduction happens at the cathode, oxidation happens at the anode. Alright, so this is what's going on right there. So the electrons are going to flow into the positive side of the battery and replenish the electrons that are being lost, because as soon as you hook this up to the battery, electrons start being pumped into the cathode side. In this case, the cathode is a piece of metal. It can be an iron ring that you want to gold plate. It can be a key. It can be anything that is metallic that will conduct electricity, will work as an anode. As a cathode. This is where electrons are pumped into. The cathode becomes negatively charged because of all the electrons. So as it does that, it will repel the negative ions that are naturally found in the liquid. The liquid we're going to be using is copper sulfate, copper 2 sulfate. Why are we going to use copper 2 sulfate? Because it's cheap and it's a good source of copper. If you wanted to gold plate something, you would need to use something that has gold ions in it. If you wanted to silver plate something, you would use something that has silver ions in it. In our example, in our lab, we're going to use something that has copper in it, and that's copper sulfate. So when this becomes negative, the sulfates will try to get away from the cathode. But because it is negative, it's going to attract copper ions to it. The copper ions will be instinctually, mysteriously attracted. They don't know why. They're going, ooh, what a pretty nail. What is it about that nail that I like so much? I must go and investigate. The reason is because that nail is negatively charged, and they are positively charged. They don't know this. Don't tell them this. So as they become strangely attracted to it and come near and touch it, at that point, the copper ions, which were very happy, have 2 electrons rammed into them, thus becoming copper solid. So in a few seconds, you start seeing copper appearing on the surface of this iron nail. Okay? This does not work naturally. Okay? You need a battery in order to force this to occur. This is electrolytic cells. So this is stuff that you must force to happen using a battery. Now, what are batteries? Batteries are about 2,000 years old. We discovered batteries a long time ago. So you need to draw, I'm going to erase the stuff that I will eventually draw. You need to draw the rest, please. Actually, you know what? It might be easier just to start fresh. So draw 2 beakers. You need a sheet of metal on one of them, sheet of metal on the other, a wire connected to a little light bulb connected to the other sheet of metal, some solution, this is going to be called the anode, this is the cathode, then you have what is called a salt bridge connecting both of these. In the salt bridge you will have some sodium ions and some nitrate ions. The solution is going to be filled with zinc ions and nitrate ions. This solution is filled with copper ions and nitrate ions. This piece of metal, your anode, is zinc. This piece of metal is copper.
Is that a little light bulb?
Yes.
Not really good at
All right. So, what happens at the anode? The anode, you're going to need a metal that is higher up on the chart. If it's not higher up on the chart, it will not work as an anode. Zinc is higher up on the chart, so it's going to want to give electrons. When zinc gives electrons, it becomes zinc plus 2. And electrons are produced and come out the wire. These electrons will do work for us. Maybe they'll run our calculators. Maybe they'll run a flashlight. Maybe they'll run our iPhones. And they'll come down here to the cathode and fill the cathode with negative electrons. The cathode is now negative. So here at the anode, zinc is oxidized. That means zinc loses 2 electrons. So more and more zinc ions are being produced. Okay, as the cathode becomes more and more negative, it's going to strangely, wonderfully attract the copper ions to it. And once again, as the copper ions touch this piece of metal, they'll get stuck there because at the cathode, the electrons are picked up. So copper ions will get reduced, red cat, by 2 electrons at the cathode. So, as this happens, more and more of these copper plus 2 ions get reduced and disappear. Now, what starts happening? You get more and more positive ions being produced. So what starts happening to the anode side? It's beginning to become more positive, more positive. That's very bad because electrons always want to go toward the side that's positive. And this side used to be the positive side. But now this side is becoming more and more positive. So there's an imbalance. So you'll start seeing your battery begin to die. There is a way to keep the battery going, and that's through your salt bridge. If this side is becoming too positive, which one of these 2 ions should flow over in order to neutralize it. The negative nitrate flows over and neutralizes the positivity here by adding more NO3 minus. Okay, so what starts happening to these copper positive ions on this side? They disappear, leaving behind the negative ions. Well, if that side becomes too negative, then why would the electrons flow over there? Electrons don't like other negative things. So what does the salt bridge do in order to ensure that this side does not become too negative? The sodium positive ions will flow over and neutralize, thus ensuring that that side doesn't become too negative. And that is how a voltaic cell works. Now I want to show you how a battery works so that next time you use a battery, you'll be a little more cognizant of what magic is going on in there. Same principle involved, just manufactured in a different way. This is called a dry cell. You can if you want to. If you don't want to, don't. I mean, this is for your own education. This is not going to be on the test, but you know what? You're going to be using these batteries for the rest of your life, probably. It'd be kind of neat to know a little bit about how they work. Okay, so on the outside, you have, if you've ever taken apart a battery, you know that there's a shiny metal on the outside. That's zinc. That's zinc. That is your anode. So the zinc, the shiny outside is your anode. Down in the middle, you're going to find a piece of graphite, carbon. Okay, that is your cathode. Now I'm going to simplify things. They get a little more complicated. If it's an alkaline battery, there may be some calcium sulfate paste along with ammonium sulfate paste. That's why they're called alkaline, because they have these calcium ions or magnesium ions on there. And magnesium and calcium are alkaline. This is a paste. Has anyone ever taken apart a battery or have seen a battery blown up?
Yes.
You know, there's a white paste. That's what's on there. So, the zinc is going to produce electrons. And those electrons will come out of the flat side of the battery. They will only come out of the flat side if you have ensured that they have somewhere to go. So if you put in a battery only the flat side down, they're not going to come out because the electrons must have a pathway to get back to the other side. They must have somewhere to go. We call that a circuit. So unless it's connected to a circuit, it's not going to go anywhere. So when you connect both sides to the circuit, then electrons come out, do their thing, and then come back and, okay, so here the zinc solid becomes zinc plus 2, leaving 2 electrons. That is your anode. Over here, this is the part that's a whole lot more complicated. Just imagine that carbon absorbs the electrons, okay, becomes stuff carbon negative. It's not that simple. It's a little more complicated, but I'm going to confuse you if I try to give you what really happens. So there, let's just say carbon is going to be reduced. So that's where the electrons accumulate. As this graphite rod becomes too negative, why would the electrons want to go there? So what happens is positive ions will flow toward it and absorb it. Absorb the electrons, reducing its negativity, making it want to continue working. This paste is, in essence, your salt bridge. That paste is your salt bridge that causes the battery to keep going. Now, have you heard of rechargeable batteries?
Yes.
Okay, so in a rechargeable battery, you basically force the electrons to come back out and go back and reduce what was formerly oxidized. Simplifying a little bit, not all the electrons can be recovered back out and recharged. So every time you recharge your battery, it's not going to last as long. Okay, that's just part of it. It's getting better. Every new generation of phone batteries lasts longer, but that's always going to be a problem until they find a different way to create an electrical power source. All right?